Professor Carlos Plain from Durham School says, "I've dedicated my entire career to making a clear theory about the universe. Then, something happens. The theory is being closely examined. I accept this challenge because it's through such scrutiny that we make progress in science." The James Webb Space Telescope is changing many long-standing beliefs in cosmology that have been accepted as truths for many years. A new image has shown that we made mistakes in space science. The telescope, which was designed to explore the center of galaxies, is actually revealing surprising results. These findings could lead to a whole new understanding of the universe. Not all scientists are upset by these new discoveries. Many are welcoming these changes because it's been clear for some time that our previous ideas had problems. The unusual behavior of the universe's expansion rate should have raised concerns for experts long ago. However, many continued to stick to old theories. The cosmic microwave background radiation, CMB, is the oldest light we can detect, created about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to form stable hydrogen atoms. This process, called reionization, made the universe transparent to light. The CMB was first discovered in 1964 by American scientists Arnold Penzias and Robert Wilson, who were working with new radio equipment. They detected a constant noise coming from all directions. This discovery was initially seen as strong proof for the Big Bang theory. Penzias and Wilson won the Nobel Prize, and their discovery became a key moment in the history of space science. The CMB offers a snapshot of the early universe, with tiny temperature variations providing important clues about conditions shortly after the Big Bang. Scientists have used the CMB as a reliable tool to measure various aspects of the universe, including its rate of expansion. In the late 1920s, Edwin Hubble made similar measurements. He observed that distant galaxies were moving away from us, and their speed was linked to how far away they were. This relationship is now known as Hubble's law. Although Hubble's measurements were less precise than those made today, they were groundbreaking. After the CMB was discovered, scientists recalculated the universe's expansion rate, finding it to be lower than Hubble's initial estimate. Later calculations using type Ia supernovae as standard candles gave a more accurate measurement. However, discrepancies remained, and the difference in expansion rate measurements has been known since the 1990s. Scientists have wondered if there are issues with the CMB data or if the laws of physics might be different than previously thought. This issue, known as the S8 tension or Hubble tension, suggests that our current understanding of the universe might be wrong. Since the James Webb Space Telescope, JWST, began its mission, it has provided groundbreaking data that could help explain these issues. Some galaxies are so old that their formation might have started before the Big Bang, challenging old scientific theories. Space science is now facing what is considered the biggest crisis in modern cosmology. The rate of the universe's expansion and how we understand the origins of everything are under serious examination. New images show a universe that is very different from earlier models. The S8 tension has acted as a warning for scientists who still cling to outdated ideas, now struggling with the realization that our understanding of the universe might be incomplete. This uncertainty has left many researchers feeling disheartened. To solve this crisis, we need to understand how science works. Theoretical scientists use a mix of mathematical models, observations, and reasoning to form conclusions. Their understanding comes from noticing patterns, testing hypotheses, and performing theoretical analysis. The term theory itself suggests progress and ideas rather than absolute facts. Our knowledge comes from images taken by telescopes, sound waves, radiation detected by radio telescopes, and data from neutrino and gravitational wave detectors. The James Webb Space Telescope allows us to break down the oldest light into individual frequencies and study it in detail. It can show what existed in galaxies billions of years ago, their mass, and the number of stars they contained. However, Webb's images do have limitations. For instance, it cannot detect galaxies or black holes that appear bright due to gravitational lensing. Our understanding has progressed to consider many possible explanations, often rejecting alternative ideas. New discoveries from the James Webb Telescope provide crucial clues that could replace old theories with fresh insights. Scientists are now grappling with these discoveries, which are so unexpected that finding new explanations is challenging. These findings are shaking the foundation of physical science, raising concerns among some experts. The laws of physics we follow today are still largely based on Isaac Newton's 17th-century work. For centuries, Newton's laws of motion and gravity have been the basis for understanding the physical world. His laws work well on Earth, but in space, his ideas were expanded by Albert Einstein in the 20th century. Einstein's special theory of relativity, published in 1905, changed how we view reality, showing that the laws of physics depend on the observer's movement. His general theory of relativity, published in 1915, extended these ideas with complex equations describing how mass, like stars or galaxies, bends spacetime. While Einstein's theories have been proven true in many areas, he knew they had limits and sought a unifying theory that could explain everything. No scientist has yet succeeded in this search. It's interesting to think about where mistakes could lie. Michio Kaku, a famous American astrophysicist, suggested that solving this issue could lead to a Nobel Prize. We need to explore where our understanding might have gone wrong, whether we misinterpreted phenomena or if the telescopes themselves might be at fault. Dark matter and dark energy are major suspects in the cosmological crisis. Current models suggest that dark matter and dark energy make up about 95% of the universe. Neither has been directly observed or proven to exist. They might not even exist, or they may have properties we don't yet understand. One possibility being explored is that dark matter's properties may have changed over time, perhaps offering new insights into gravity, which interacts with mass or spacetime. Gravity hasn't been proven to act exactly as we expect. However, the reality of spacetime bending, as proposed by Einstein, has been confirmed multiple times. We cannot completely rule out the possibility that gravity has surprising properties or that another unknown effect is influencing gravitational forces over time. Certain constants in cosmology and space science have been considered universal truths because of their consistency. Research suggests that small changes in these constants could offer new insights into the universe, potentially explaining phenomena without dark energy. It's also possible that we have misunderstood light movement, leading to wrong distance measurements and galaxy ages. Maybe our assumptions about the universe's early conditions were wrong, or we misinterpreted the cosmic microwave background radiation. It's even possible that the universe doesn't come from a single starting point, challenging the Big Bang theory. Even small mistakes in the Webb telescope or other instruments cannot be ruled out. Some experts believe that errors in equipment, data processing, or interpretation are always possible. The continuous reevaluation of cosmological theories shows the essential nature of scientific progress, the ability to adapt and improve our understanding based on new evidence. The James Webb Space Telescope's observations represent not just a technological leap, but a key moment in our quest to uncover the universe's secrets. As we examine these findings, we must keep in mind the larger context and the implications of such changes in cosmology. The process is driven by the need to update theories in line with new discoveries. Finding unexpected anomalies can be unsettling, but it also presents an important opportunity for scientific growth. Theoretical models in cosmology are meant to provide a framework for understanding the universe's origin, development, and future. However, as new data emerges, these models need to be tested and revised to incorporate new insights. One key area is dark matter and dark energy, which are central to modern cosmology. Dark matter, an invisible substance that doesn't emit or absorb light, was proposed to explain differences between observed galaxy movements and the mass expected from visible matter alone. Dark energy was introduced to explain the universe's accelerating expansion. However, despite their importance in current theories, both remain mysterious, and efforts to detect them on Earth have so far been unsuccessful. This has led researchers to explore new theories and potential explanations. The challenge of understanding dark matter and dark energy is magnified by the vast distances involved in cosmological studies. The cosmic microwave background and other features provide indirect evidence of these components, but their elusive nature remains a mystery. This uncertainty has encouraged scientists to consider a range of possibilities, from changes to current models to entirely new laws of physics. Some theories suggest that dark matter might consist of different kinds of particles than previously thought, or that dark energy could represent an entirely new force. Another exciting area of study is cosmic inflation, the theory that the universe expanded rapidly in its earliest moments, creating the large-scale structure we see today. While inflation theory explains many features of the universe, it also raises questions about the nature of this rapid expansion. New observations that challenge inflation could lead to changes in how we understand the early history of the universe. Finally, the search for life beyond Earth remains a major focus of space exploration. The discovery of exoplanets, planets outside our solar system, has opened up new possibilities for studying conditions that could support life. Advances in telescope technology, such as the James Webb Space Telescope, allow us to explore these planets for signs of life. The discovery of life elsewhere in the universe would have profound implications for how we view our place in the cosmos. In conclusion, the ongoing reevaluation of cosmological theories highlights the strength of the scientific method. The James Webb Space Telescope and other advanced instruments have provided amazing new insights into the universe, prompting scientists to revisit and refine old theories. This continuous process of inquiry and correction is vital for advancing our understanding of the universe and answering fundamental questions in cosmology and space science. As we continue to explore the universe, we remain committed to discovering new knowledge and inspiring future generations to expand the limits of human understanding.